Hey folks, this is Scott Weingart, and you're listening to the EMCrit podcast. We are back with more acid base. This is part 2 of what I now think will be a 4-part lecture series on acid base. Let's review what we talked about last time. So last time we determined that there are really only 3 things that determine acid base, and they are carbon dioxide, the difference between your strong ions, and then your weak acids, things like albumin. And that's it. Those are the only 3. What we used to think determined acid base, like H plus or bicarb, are actually dependent variables. And infinite amounts of bicarb can be formed or disappear depending on what else is going on with the other 3 things we just mentioned. We figured out a way to split up the respiratory and metabolic acidoses. And the way we're doing that is by looking at base excess, aka base deficit. We said that the normal base excess is -2 to +2, and whenever you're outside of that range, something is going on. And what that something is going to be predicated on the strong ions we can measure, which is essentially sodium and chloride, which make up the strong ion difference, and then our friend lactate. It's made up of weak acids, primarily albumin, or it's made up of strong ions we can't measure, things like keto acids, or in the toxicologic world, things like aspirin, but that's it. And so our goal when we see a large base deficit is to figure out how to fill it, to figure out what's going on. Can we explain it totally on the things we can measure, or are there unmeasured things occurring? And that's what we're going to talk about today. Now, for this lecture to work, you really want to go to the show notes and print out the acid-base sheet and follow along as we talk for this particular portion. I know some of you listen in your car and that's not going to be possible, and you'll still get a bunch out of this, but then when you get to the hospital or back home, print out the sheet and try to review what I was talking about. All right, now this is a sheet that'll take you through acid-base problems. And when you look at it, you're going to say, oh my God, he's out of his friggin' mind. There's no way we're going to be doing this. But what happens is, after you use this a couple times, what you'll realize is that it becomes intuitive and you're not doing calculations anymore. You understand it and therefore don't need to have this sheet. You don't need to be doing numbers because things are just making sense intuitively, or at least I think that could happen for you. I will tell you that it took me 6 months during fellowship to get this quantitative theory of acid base. And I actually was motivated to learn it. So that right there is going to affect how long it takes. But there was no one to teach me. So I had to learn on my own. So maybe having this lecture will cut down that time a little, because I didn't have a lecture like this, but not a lot. It still requires a lot of thinking. And it might be not worth it to you. You might want to stick with not understanding acid base and just letting the renal guys come down and tell you what the patient actually has. But that's not acceptable to me. I can't stand not knowing things. So if you play it this way, you will understand acid base, and then therefore you won't have to remember formulas anymore. So step 1 on this sheet is get labs. Well, that's easy, but a lot of times I don't see the labs we need. If you have a patient you know is going to have an acid-base issue because their VBG had a pH of 6.9, then you have to send the rest of the stuff. And the rest of the stuff is lactate, albumin, acetone, and a chemistry. And you want them to be as coincident as possible. It's okay if they're off by a half hour or so, but if it was 5 hours ago you had your chemistry, you really should send another one with your ABG or VBG. Step 2 is you look at the pH, and you know this part. If it's greater than 7.45, you say the patient's primary issue is alkalosis, and if it's less than 7.35, acidosis. Easy. All right, now we get to the stuff that's a little bit different. So step 4 is calculating the strong ion difference, and all you do is you subtract your chloride from your sodium. If it's less than 38, then they have a strong ion difference contribution to their acid-base problem.
And since we said the normal difference between sodium and chloride is 38, so a normal sodium 140 and normal chloride about 102, difference between them 38, if that difference is smaller, it means the patient has an acidosis. And we could call it a strong ion acidosis, or we could call it a hyperchloremic acidosis. But regardless, that is contributing to the patient's acidosis.
And that means they have a metabolic acidosis. And now why could that happen? Well, it could be that you gave a fluid that led to this, and we'll talk more about that. But any fluid whose SID, meaning the sodium, the chloride subtracted from the sodium of the fluid itself, is less than 24 will eventually lead to acidosis. We'll talk about that. You don't need to remember that. They might have a renal tubular acidosis or they might have diarrhea. All right? If their SID is high, meaning they have more sodium than you would expect in relation to their chloride, then that means they have a metabolic alkalosis contribution. And that could be from nasogastric suction, diuretics, hyperaldosteronism, volume depletion. Great. All right. We're going to go through this in a little more detail when we get to the real cases. All right, step 4 is look at the lactate, because that's not part of that unknown anion. We can measure lactate. So if it's greater than 2, then they have a high lactate. If it's greater than 4 and they're infected, start early goal-directed therapy. And if you don't think they're infected, then there's a whole host of things that could cause it, and they're all listed here. Ruben Almeida and I just sat down, we brainstormed all the possible toxicologic causes of an elevated lactate. So these are not the ones that just will give you an anion gap. These are the ones that are giving you an anion gap because of elevated lactate. And that's important because a lot of the unknown acids aren't really unknown. They were unknown in the 1940s when you couldn't measure lactate. Now you can. All right? So next step, step 6, is calculate the strong ion gap. And this is where people get really dismayed. There's a whole bunch of math here. And it's math only to have it down there for the first few times. Because once you get this, then you don't have to have this equation anymore. You just do it in your head. But let's say I told you that I have a base deficit of 15. Now, first off, what does that mean?
So a base deficit of 15 means you're missing 15 of base, or you have 15 extra of acid than you should. The whole purpose of this formula we're talking about is to figure out where that 15 came from. What is the source of that acidosis? That base deficit of 15 means you have 15 of extra acid you need to account for.
So if you have a 15 as your base deficit, and the next thing you do is you try to account for that by your SID issues. So you take whatever your SID is and you subtract 38 from it. Because if they had no SID issues, when you subtracted 38, the SID would disappear, right? Because a normal SID, 140 minus 102, is 38. You subtract 38, the SID is not contributing to that base deficit. But let's say instead their sodium was 140 and their chloride was 115. So what's the difference between them two? Difference is 25. We said the difference should be 38. So we take 25 minus 38, and we get what number? Get minus 13, right? All right, now what is that really saying? Why is that math there? It's saying that of that 15 base deficit we started with, 13 of it knocked out right away because we know the cause, it's because their chloride's too high. And now we only have 2 left over that we can't explain. Then we do the equation for the albumin. And here's where it gets a little complicated to remember. You have to think through a few times. But let's say the albumin was normal. Let's say the albumin was 4.2. That means it has no contribution. Wonderful. Let's say the albumin was high. All right? If the albumin was high, what is that going to do to that unexplained base deficit? It's going to explain it to some extent, right? Because if you have acid, by the albumin being high, that's explaining why the patient has a metabolic acidosis. Does that make sense? All right. So this number just allows you to change that albumin into something that will fit into that same base deficit formula. So the number is you subtract the albumin they have from the normal albumin, so 4.2 minus whatever their albumin is, and then you multiply that by 2.5. That's the conversion factor. So let's say in this patient their albumin was 5. Let's say 5.2 for the sake of easy math, right? So we take 4.2 minus 5.2, right? And that gives us minus 1. And we multiply that by the 2.5, which is that conversion factor. And now it means 2.5 of that base deficit is filled by that extra albumin. And if we did this entire equation, and let's say their lactate was normal, we'd realize that their entire base deficit was filled by their chloride problem and their albumin problem, and there is no strong ion gap. The strong ion gap in this case would be minus 0.5,
it means you don't have to go looking. You have a complete explanation for the patient's acid-base status. All right? If on the other hand, the albumin was low, let's say the albumin was 2.2, and you did this math, what you'd realize very quickly is that the albumin is 4.2 minus 2.2, it's minus 2 times 2.5 is minus 5. It means you actually have to increase the amount of unexplained acid that's going on. Because instead of that base deficit being 15 minus the 13 explained by the chloride of 2, you now add an additional 5. And that means there's 7 unexplained acids that are hanging out that you have to go looking for. I know this doesn't make complete sense. It's going to. We're going to do some problems with actual numbers, and you'll see it.
So the last part of the strong ion gap formula is to subtract the lactate, and that'll be the final part. Now, what does this strong ion gap mean? Well, we've discussed what strong ions are. They're anything that disassociates fully when put into the plasma. Now, here's the thing. Some of these strong ions we can't measure. And as a result, if this strong ion gap formula reveals there is still a strong ion gap, it means there are some of these unmeasured anions, assuming the strong ion gap is positive. Rarely, like incredibly rarely, the strong ion gap will be negative. And a few of the things could do that are going to be anything that are positively charged ions. For instance, profound hypercalcemia, hypermagnesemia, profound hyperkalemia, immunoglobulins in multiple myeloma, bromide poisoning, lithium poisoning, or nitrate toxicity. These things can cause a negative strong ion gap, but 99% of the time, the strong ion gap is either going to be normal or positive. And when the strong ion gap is positive, it means there's a gap, and that gap is unmeasured anions, things like keto acids, or in the toxicological world, things like aspirin, ethylene glycol, methanol, propylene glycol, iron, INH, and I've never seen it, but paraldehyde. All these things will give you a strong ion gap, not explained by the SID, the albumin, or the lactate.
But at the end of it all, if after you do these calculations, you do have a strong ion gap, then you got to go looking. And on this sheet is listed the possible causes of a strong ion gap. Now, I will tell you this looks crazy, but I do this on every single blood gas I get, and it takes less than 2 seconds, and that's because intuitively I get which way all these numbers affect it. So I'm not doing this equation. What I'm doing is I'm getting a base excess on the lab, and I'm saying, oh, that's a base excess of 10. I got to figure out where that 10 comes from. And so then my next step is I look at the sodium chloride difference and I say, oh, well, that's explaining some of it. And now I have a number that's still left over. And then I look at my albumin and I'm like, oh, well, that not explaining any of it. And then I'm getting that final number for the strong ion gap, and I know whether or not there's additional problems. And that takes no time at all. But you have to understand this all to get to that point.
Now, let me make sure you folks understand what I mean by that. I am not sitting there with a calculator and a pen and pencil and a piece of paper calculating this stuff out on every blood gas I get. That would be torture. When you get familiar with this, what happens is you see a number on the base deficit on the blood gas, and that number's abnormal. Let's say it's 20. And now I just glance over at the sodium and chloride, and I realize that that chloride is higher than it's supposed to be. And just knowing that it's supposed to be 38 difference, and I see that it's actually 25, I say, oh, that's 13, and I just take 13 away from that 20. That's just in my head. I just subtract the 13 from the 20. And now I'm saying, wow, I have 7 left over. I better go check my albumin. And now I realize, oh, look, my albumin's lower than it's supposed to be. And it's lower by 2. And now I multiply by 2.5, and that's 5. And now I say, oh, crap, I thought I was down to 7, but I'm not. I actually have 12 of unexplained acid. So now I'm just looking at that lactate, and that lactate is 6, and I'm feeling pretty good because now I could take 6 away from that unexplained 12. But
oh gosh, there's still 6 left over. And now at the end of all that, in my head, I'm saying there's still 6 millimoles of unexplained acid, and I got to figure out why. Is this patient hyperglycemic and possibly that's keto acids? Well, let's look at the acetone. Or, oh no, they're not. Why would they have keto acids? So now where's that 6? Where's that 6? Or is it a toxicologic cause of that 6? And that's how I'm doing it. I'm not doing these calculations. I'm not asking you to sit there with a calculator and do these calculations. Just have the formula there because you have to understand how these things relate. And once you do, you'll be doing this in your head. And you might be saying, I'm never going to be doing this. And that might be the case. But I'm going to explain very shortly how the anion gap that you are calculating right now, hopefully, is exactly the same as this.
All right. Step 7 is think about compensations. I'm not even going to talk about that because for the most part it doesn't do anything good clinically, but I have to put it there so the Henderson Hasselbalch guys with their Winters formula don't get in an uproar that we're ignoring whether something's a chronic or acute respiratory acidosis, based on what the bicarb level is. And they get crazy if you leave that out. And then they tell you, oh, well, that's why Henderson Hasselbalch's really good is the quantitative approach doesn't deal with compensations. It does. It's just that clinically, there's no relevance to them for us in critical care or the emergency department, so we choose to ignore them. But they're there for you. And then step 8, if you have an unexplained strong ion gap, or in your minds right now, an unexplained anion gap, you got to go the step further and calculate the osmolar gap to see if you're dealing with a toxic alcohol or not. All right? Now, I know that's tough. You're going to have the sheet. You're going to try it on some acid-base problems on your own. But let's go through this, and hopefully it'll make a little more sense at the end. So let's come back before we get to the case examples for why Henderson Hasselbalch sucks. So the steps necessary to use it correctly are not prescribed and rarely performed. Now I told you a lot of extra stuff you have to do for this quantitative method. It seems kind of annoying, and you don't have to do that with the Henderson Hasselbalch generally, right? They don't tell you that. And we'll see why that's not true in just a sec. In its current form, it's inaccurate. Now why is Henderson Hasselbalch the way you've been doing it inaccurate? What does it not take into account? Albumin. It ignores the albumin entirely. Let's see how that plays out. All right, here we got a guy, pH 7.3, base excess minus 10. His sodium chloride difference, his SID, is 25. All right, what's his acid-base problem? You could say he has a SID acidosis, right? Just looking at this, and maybe that's what makes his pH what it is, and maybe he has some respiratory compensation for that. His CO2 is a little low. And great, so here's patient B. Same exact numbers. What's his acid-base problem? Well, you're going to say the same thing, right? But then you add albumin to the mix, and now patient 1, albumin is normal. And so exactly what we said is what's going on. He has a very slight SID acidosis. Maybe his kidneys aren't working. Maybe he has a little bit of diarrhea, and that's all this is. And he has a little respiratory compensation for that diarrhea, which is causing him to poop out some H+. Great. But then we look at patient B, who had those same initial numbers. His albumin's 1.5, which means that when we actually calculate the SID and put it into that base excess, there's actually a whole bunch of extra we weren't looking at. Let's go through this. So if we were to use the sheet, our first thing would be look at pH, 7.3. What does that tell you? Acidosis. Great. What's step number 2? You look at the CO2, and from this you'd say for some reason he has a respiratory alkalosis. We don't know if that's compensation or not. We don't care. We just know it's there. What's step 3? Calculate the SID, right? What's the SID? 25. Okay, so we have that in our head. We now know since that's less than 38, there is some degree of SID acidosis, all right? Or what you guys would call non-anion gap acidosis in your old system. All right, now the next step is to calculate the SIG, or to get the lactate. Lactate's normal, all right? So you get a SIG, and now you do the numbers, okay? So what's your base excess? Minus 10. So what's your base deficit? 10. All right, so now we have our 10, and we want to go 38 minus what our SID is. So we said our SID is 25. And so now we have 10 minus 13, right? Does that make sense to you guys? Are you with me? All right, so now minus 3. All's well in the world right there, because you're allowed to vary 2 to minus 2. That would all be fine. And we could just stop there. until we get the albumin, right? Now we put the albumin in the mix, right? And we say 4.2 minus 1.5, or 1.5 minus 4.2, just to make the numbers work out. This is what I mean about it intuitive. I don't have to worry about plus and minus signs because I know albumin is an acid, and therefore I know how it's going to factor in. But you guys could work it out exact numerically. But I know I have 2.5 missing of my albumin multiplied by 2.5. What's 2.5 times 2.5, guys? You got the calculators? No? Oh, okay. So 2.5 times 2.5 is somewhere around 7, right? 6 point something or 7. So now that 7 gets added in to that minus 3, and now I'm back to having a deficit of 4. I have a sig of 4 at the end of that equation. That's a problem. And it's a bigger problem because I know it's not lactate. I've already done the lactate. So now I have 4 of acid unexplained. Does that make sense? Are you guys getting that? Even though those numbers, until you had the albumin, look the same. In the first case, everything worked out fine. In the second case, the guy's actually acidotic. So albumin matters, and that's why Henderson-Hasselbalch fails without putting albumin in the mix. All right, the next thing to understand why Henderson-Hasselbalch is idiotic is there's no such thing as a normal anion gap. Well, what have you guys been told is the normal anion gap? 12. That's what they always say, 12. Time to understand what the anion gap is. What is the anion gap? What's that, bud? Albumin. That's it. That's what the anion gap is. That's why this is such an idiotic system. Is they're telling you use this arbitrary number of 12, and they're telling you to use it in the critical care guy who's been there for 4 weeks and their albumin is 2. They're telling you to use it in the profoundly dehydrated guy, the albumin is 6. There is no such thing as an anion gap. What the anion gap is your albumin. It's also a little bit of your phosphate and a little bit of your lactate, but for the most part, it's your albumin. And your normal albumin is 4-ish, right? And we said the conversion factor is 2.5, so what's 2.5 times 4? It's 10. What's your normal anion gap? 12. Well, what's the other 2 from that 10? Lactate is usually 1 in a normal patient, or 0.5, and your phosphate, which accounts for 1 of your anion gap. So anion gap doesn't make sense. What makes sense is...
Now, we should go over that again because this is probably one of the most important points in this part of the lecture. So there used to be a time where it was really hard to measure albumin, and therefore they had to make this arbitrary anion gap of 12, which is predicated on a normal albumin. But we are in the 21st century now. We can measure albumin. So there is no such thing as the normal anion gap being 12 anymore. We know where that 12 came from, and we know it's not going to be appropriate in a patient whose albumin is not normal. But let's go through it one more time where that 12 came from. The 12 they had was because if you take the normal albumin of 4, 4.2, and you can do the conversion factor at 2.5, it comes out to 10. So 10 of the 12 they're asking you to use as the normal anion gaps from albumin. One of it is from the normal lactate, and one of it's from the normal phosphate, which we don't even bother to calculate. That's where that 12 comes from. Now, the problem with using that in acid-base formulas is that some patients won't have a normal albumin. And if you do have a patient who has a very low albumin, then their normal anion gap should be very low as well. If you have a patient with a very high albumin, then their anion gap should be high. And so using 12 in those patients is going to be inaccurate. All right, folks, so that was part 3. That is definitely the most confusing part of all this. And as we go through the last 2 parts, I think it's going to start making more sense. So here's what I think we should do. I'm going to put one acid-base problem in the show notes. If you like, print out the acid-base sheet and work through that problem. And then in part 3 of the lecture, I'm going to go through the answers. So I think this will be the most effective way to learn this stuff is look at the problem in the show notes at EMCrit.org, print out the acid-base sheet, work your way through it, and then when we get to part 3, you could see if your answers matched mine. In the meantime, if you have any questions about these first 2 parts, send them to me by email or through the web page or on the Facebook page. And what I'm going to do is I'm not going to reply to you probably right away personally. What I'm going to do is I'm going to take all the questions I get and add them to the part 3 of the show so everyone could benefit from them. Now, just before I go, I have a few shout outs and things to let you know about. First of all, Alex from the Air Medical Memorial sent me a t-shirt, and I just want to let you folks know what this is all about. This is for our fallen brothers and sisters who worked helicopter and flight EMS
and perished in the line of duty. And there's a memorial for them at the base of the Rockies. It's at airmedicalmemorial.com, where you can find information about this. It's a worthy cause, and it's honoring our colleagues. So thank you, Alex, for that t-shirt. Josh Mullarella let me know about a free iPhone app called ERRES, E-R-R-E-S. You could search for that in the iTunes store, free of charge, and it's geared specifically to emergency medicine residents. Check it out. Casey Parker in Australia has started a new blog for outback emergency medicine and critical care aficionados. It's pretty good. It's in its beginning stages, so there's just a few posts up, but they're worth reading. And the URL is a little complicated, so you go to the show notes for that, or search for Broome Docs, B-R-O-O-M-E Docs. And then last but not least, my listener Ivor Kovic sent me a notification that he's developed a CPR application. And this one is for fee. It's $1.99 in the iTunes store. But he sent 3 codes so that folks could check this out. Now, I'm going to give those away. And the way I'm going to do this giveaway and all giveaways henceforth is you need to be signed up to the email list. So that's where I'm going to pick 3 folks from and send them codes for this application. So you need to be signed up on that email list. If you're not already, go to the EMCrit.org page, and on the very top is a blue bar. That'll send you a link, send you to a link where you could sign up for the email list, or at the very bottom of the page as well, it says sign up for email updates. Go to one of those 2 and put your name on the list. I will never spam you or sell your email address to anyone, I promise. All right, that's all for this week. We ran a little long. Hopefully it was worth it. And so I will talk to you soon. Have a great week.